So you can go ahead and pause this video at this moment if you need to check your answers for the 4 problems, the 3 out of 4 problems that you did. They're listed here. So this is number 42, 50, 52, and 56. All right, the last part 3 of this video, we're just going to go through some example problems. So the first one we're going to look at is this situation of scrambled eggs. So I don't know if you go grocery shopping ever for your family, but I know I do, and I always have to check to make sure that when I buy my eggs, that there aren't any broken eggs inside. And so basically what we found is that the mean number of broken eggs is actually 0.6 with a standard deviation of 0.5 eggs. So if you buy 1 dozen eggs, there's a likelihood of you're expected to have a broken egg 0.6 times. All right, so how many broken eggs do you expect if you buy 3 dozen eggs? Well, the answer is 1.8. The question is, how did I get that? Well, this is a transformation problem. So I just took 0.6, which is the mean, and I times it by 3 because I'm getting 3 dozen eggs, and that's where I got 1.8. So please remember, when you see what do you expect to get, another word for that is mean. Now they're asking what's the standard deviation if I buy 3 dozen eggs. Well, I know the standard deviation if I buy 1 dozen eggs is 0.5, so I'm going to multiply that by 3, and that's where you get 1.5. Okay, so what assumption did you have to make about the eggs in order to answer this question? Well, you had to assume that they were independent, that having a broken egg is an independent event that's not dependent on anything else happening. Like the whole shipment has an equal likely chance of having a broken egg. It doesn't. They're all in the same packaging, things like that. So there's nothing else that's affecting the broken eggs. Okay. Let's look at another example. This example is packing time. So we're saying that a company is manufacturing small stereo systems. At the end of the production line, the stereos are packaged and boxed, and then they're ready to be shipped. The company says that times required by the packing stage can be described by a normal model, so you should be thinking of a normal curve, with a mean of 9 minutes. So that's your expected outcome, and a standard deviation of 1.5. And the times for boxing can also be modeled normally with a mean of 6 and a standard deviation of 1 minute. And so we want to know, what is the probability that packing takes over 20 minutes? So the first thing we need to do is we need to find the mean of both of these situations together. All right, so let's go ahead and combine them. So we're going to look for the probability of x being greater than 20. Okay, so first thing I need to do is I need to figure out what is my mean. And so I'm going to look at the mean of the packing time and the mean of the boxing time, and I'm going to add them together. So that would be 9 plus 6. So the expected time is 15 minutes. It's expected to take 15 minutes to do both of these things. And then I want to combine my standard deviation. And so I'm going to do 1.5 squared plus 1 squared, and you should get 1.8. So with a deviation of about 1.8. So then step 2 is I want to find the probability of it taking longer than 20 minutes. So remember, it's a normal curve. So I know that my mean time now, it takes about 15 minutes, and then these go up by 1.8. That's my standard deviation. If you go this way, it's going down by 1.8. Okay? But I want to know what's the probability of 20. So I'll say like 20 is somewhere over here. That's where 20 would fall. So I want to know this probability right here. Okay? And so what I'm going to need to do is find my z-score. To calculate my z-score, I take my number of interest, which is 20, subtract out the mean, and divide by the standard deviation. And you end up with 2.77. Okay? So then I got to go to my handy dandy table, which is, let's see, is this it? This is it. And I'm looking for, let's see, 2.77. So here's 2.7. That's 0, 1, 2, 3, 4, 5, 6, 7. So I'm looking at 0.9972. So remember that as I go back. So it's 0.9972. Now, 0.9972 actually represents everything that is less than 20. So in order to get everything that is greater than 20, I just simply take 1 away from that, and I end up with a final score of 0.0028. So this part right here is 0.0028. So there's less than 1% of a chance for it to take over 20 minutes. All right, the next problem, what I suggest you do is read through the problem and see what you can do on your own. So pause the video or stop the video at this moment. See what you can do on your own, and if you're struggling, then come back and watch the video for some extra help. So this is how much cereal can be poured into small bowls, varies with a mean of 1.5 ounces and a standard deviation of 0.3 ounces. A large bowl holds 2.5 ounces with a standard deviation of 0.4. So you're going to open a new box of cereal, and you're going to pour 1 large and 1 small bowl. So how much more cereal do you expect to be in the large bowl? Well, all you have to do is take, if you're looking at expect, you should be thinking mean, right? So you're going to be just taking 2.5 minus 1.5. And that's 1 ounce. What's the standard deviation of this difference? Well, once again, for standard deviation, you have to square it to find the variance first. Then you add. You never subtract the standard deviation. So you do 0.4 squared plus 0.3 squared. And then you're going to take the square root of that to get your standard deviation, and you should end up with 0.5. And it is in ounces as well. Okay. So if the difference follows a normal model, what's the probability that the small bowl contains more than the large bowl? And so what we're going to look at is we're going to look at our mean value of 1 ounce. And then again, it's going to go up by 0.5. Or this way, down by 0.5. Now we want to know the probability that the small bowl contains more cereal than the large one. So our interest is here at 2.5. So we want to know this probability here that there's more. Okay, so what are we going to do? We're going to take the expected value of a large bowl of cereal, which is 2.5. We're going to subtract out a small bowl of cereal, which is 1.5, and divide it by our combined standard deviation of 0.5. This should not be 0.2. And so you end up, this value here is equal to 2. So then again, you go to your table. When you look the table up, you get 0.9772. And again, that would be for everything that's less than. That's the probability that the small bowl is going to have less than the large bowl, right? And so there's really a small percent. You subtract it from 1, and you end up with 0.0228, and that represents this little part right here. That's your the small bowl containing more cereal than the large bowl. A couple more questions here. What are the mean and standard deviation of the total amount of cereal in both bowls? Well, this time you're going to add, but again, your standard deviation is going to stay the same. So if you're looking at both bowls, you add them together and you end up with 4 ounces. And the standard deviation is the same at 0.5. If the total follows normal, what's the probability you poured out more than 4.5 ounces of cereal in both? And so again, what you're going to do is, I'm going to draw it down here. You're going to simply draw your graph. The middle now is both together, which is 4, with a standard deviation of 4.5, so 4.5 falls here. You want to know that you pour out more than this amount of cereal in the two bowls together, so we're looking at this situation here. And so again, you want the probability of X being greater than 4.5. And you just simply take 4.5 minus 4, which is the mean, and divide it by 0.5. You end up with 1. You look that up on your table. You get 0.813. Okay, but that is going to be the area to the left. You know, this part right here. So if you want to know the other side, the part that's in red, you have to subtract it from 1. 1 minus 0.8413, and that's equal to 0.1587. So there's about a 16% chance that if you're pouring out the cereal, it'll be higher than 4.5 ounces. Right. And so we're going to stop there. You do not have to complete this last question, question F. All right. Please note you do have some practice problems to do, and those are listed right here. So you're going to do 35 through 63 odd.